In this problem, we are told that we need to write a function that generates every sequence of throws a single player could throw over a game of rock, paper, scissors based on the number of rounds passed in the function. So we know that we have the choices of rock, paper, or scissors, and then we're given a number for the function that tells us how many of those choices will go into a single game. Great. So our input is a number. It represents the number of rounds in a single rock, paper, scissors game. So the output of our function is going to be an array of arrays that looks something like this. If my rock, paper, scissors number, if the number of rounds I have is 2, we'll have a rock and then a rock, because we can play the same play twice. We don't worry about duplicates. And we'll say rock and then paper. And then next we would have rock and then scissors. Cool. And so on and so forth until we have all of our possibilities exhausted. So you notice that the output is actually one large array that contains smaller arrays. Each smaller array represents a single game of rock, paper, scissors. Now, we can have duplicate strings within our arrays, but we don't want to have 2 arrays that are exactly the same. So we should only have one rock at the end. Okay. Next. Constraints. We are told that we need to write a recursive solution. That's our only constraint. And finally, for time complexity, we'll think about that at the end. Awesome. So the way that we're going to think about this problem is like a tree. I don't want my tab size to be 8. Let's bring that down to 2. Okay. So our tree, you may be wondering, like, what is the root of our tree? Well, you could think of it like this: rock, paper, and scissors. Each of these is one of the choices that we can make. So coming off of rock, if I choose rock, then let's see, can I do that? There we go. Coming off of rock, I could have, what could I choose? I could choose another rock. Actually, that would be my first rock. Next. All right, I'm going to choose another rock. So now my final array, if my number is 2, the number of rounds I have is 2, would be rock, rock. And it looks something like that. Next, since I have one of my games, I'm going to push that into my result array of games. And I have my first game of rock, rock. Next, I need to go back to when I only had one rock in a game, and I need to, let's see if I can fit this in here. There it is. So now I need to go over here, and I need to add the next play that I can use, which is paper. So I go rock plus paper. And now this itself is a single game. So I need to add this to my output array, like rock, paper. And finally, VS Code indented this for me, so it's a bit harder to see. The last game should be rock, scissors, which you can think of it being like this. We'd have to, wonder if I can delete that. Yeah, there we go. Finally, it's so hard to put this in here. I could do 2 branches off of this, but it's a bit harder to make 3. So why don't I could do that. And then why don't we shorten this and say RP for rock, paper. And then finally, we'll do rock, scissors. So I know this isn't that easy to read, but we have rock, 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 paper, and rock, scissors. That actually takes care of all of the possibilities that I have for starting with rock. So now I would move back, or I would move to paper and do the exact same thing and add the paper possibilities to my array. So when we think about our decision here, we notice that we always go to a leaf of a tree. If you think of this like a tree where the very top is our root of our tree, and going down a branch, we have leaves. We leave a leaf when we get the length of our number, the input. So when we have 2 plays, if our number is 2, and let's just clarify that, number is 2. When I have 2 plays here, I go back up my branch to when I only have 1. And then I add the next play to that 1 branch to give me 2 plays. And now I'm done with that branch. I'm on a leaf. So I go back, and so on and so forth. So obviously our tree gets a lot bigger the more numbers we have, but the logic stays the same. So basically, we always end our traversal of the tree. We stop going down the tree when we hit a leaf. And how do we know when we hit a leaf? When our array that we're building is of the size of the number is passed into our function. Let's go ahead and start writing our function. I'm going to use an arrow function. We're going to say const rock, paper, scissors equals the number of rounds. You know what? Let's be really explicit here. They call it throws. Okay. Number of throws. Okay. So we already know from the very beginning that we need an array, a big list, to carry all of our smaller lists. So we're going to create that big list right off the top. And we're going to call it result, maybe? There's probably a more creative name for this. But we know we're going to need this, and this is where we're going to add all of our plays, our games of rock, paper, scissors. At the end, we know we're going to need to return result. So let's just write it so we don't forget. The next thing we're going to do is something that's very common in recursive solutions, which is to actually write an inner recursive function that will call itself, and it will build the result out. Let's see what that looks like. So I'm going to write another function called const recurse. Not super creative here. I'm sure you can come up with a better name for your inner function, but I don't know what it's going to take in yet. So let's just have it empty in terms of parameters. We are going to eventually invoke recurse. And I can show what would happen if we don't invoke recurse. But let's put this for right now, because what you see from lines 16 to 26 is a very common recursive pattern. We're actually not invoking rock, paper, scissors, the function, recursively. We're going to invoke recurse recursively. Okay, great. Now, going back to our tree here, we remember that we always go back up the tree. We go back up the tree when we hit a leaf. And how do we know we hit a leaf? It's when our leaf is of size number. In this case, it was 2, because this was a small tree and easier for me to type out. So we got number of throws. That's going to be our number, like the number 2 that I had before. But it could be anything, right? So when you're writing a recursive function, which this is what we're going to do right now, you have to think of when you're going to stop recursing. Because if you don't think about that, you'll end up recursing forever, because the computer never knows when to stop following your instructions. So this is often called the base case. And our base case is basically when we reach the root of a tree. So what we're going to do is basically say that when we're going to stop recursing once we reach the root of the tree. Now, I'm going to say if we haven't reached the root, we're going to do this. So we have to think about what is happening at the top of the tree going down, or even from a branch here, an incomplete branch. It's not a leaf yet, it's still a branch. So we're basically saying for each of these choices, we're going to start with that choice, and then we're going to add the other choices to it, eventually returning when we reach the root of a tree. So I'm going to say that we're going to take, I'm going to say for each choice of rock, paper, scissors, we're going to add all the possible choices after it. How do we add all of the possible choices? This is where the recursion happens. So let's go ahead and think about that for right now. With our pseudocode, for each choice, we can do this. We can make a for loop. We can loop over rock, paper, and scissors. So I actually do need to type out rock, paper, scissors because we're not given that anywhere. So I'm going to make another array here called choices, which is just rock, paper, and scissors. Okay? So we're going to go down here and we're going to say for loop. Choices. For each choice, add the possible choices after it. Okay, so we need to look at what our output is going to look like again. We notice that we have our big list of arrays, which is the array that holds everything. That's our result. But we also need to have an array for every single game. So what I'm going to say is that when we recurse, as we go down the tree, you need to actually pass down an array each time. So when I start off here on line 11, with rock, rock is going to be in an array. And then I'm going to push another rock into the array. Now, the way that arrays work, we can't just take off this rock. We can't just pop off this rock when we go back up the tree and add then the paper and then pop off the paper. We can look at what happens if we do that, but basically you're going to want an array here and an entirely different array here for rock, paper, and an entirely different one for rock, scissors, and so on and so forth for the rest of the plays. This is a different array. These brackets you can think of being totally different than these brackets. They're a different array in memory. So what do we want to do? Maybe we can just make an array. So let's say const, maybe let's call it next play equals what? It equals an array of the current choice, which would be choices at I, right? So we've got choices at I. Now, to figure out how we're going to build this, so far we have rock, which is, this is going to be our first element in our next play. So choices at I starts at rock, right? Because I starts at 0 and rock is at 0. So we start with rock. And how do we build this again? Well, this is where we call our recursive function. We invoke itself. So right after we have this array of next play, we're going to recurse on next play. So we're almost here. We're almost here. But one thing you are probably noticing, or have already noticed this, is that we actually haven't told recurse that it takes any arguments. So we need to figure that out first. Let's say that it takes the argument of our current play. And a current play is going to be an array, right? It's our current play is like this array. And then at some point it's going to be this array. And then it's going to be that array. So current play is an array. Now, what should I put down here? When I first start off, you might think, okay, well, I need to make rock the first play. But that kind of messes with our logic in our for loop because we're going to start with rock. So actually, our current play to start off with needs to be an empty array. So now we're saying, hey, our next play is a new array with choices in it. The problem is that we haven't yet combined our next play and our current play. We need to combine them, right? Because we have rock, and actually we're starting off, let me make a new line here. We're starting off with this, an empty array, as our first play. We're going to combine rock in this empty array so that we're going to have a rock like that. And then finally, we're going to combine that array with this one so that we end up with rock, rock. So we start empty, and then we add one element, and then two. So another really common pattern with recursive functions and arrays is using this. We need to actually take our current play and concatenate it with choices at I. So if you don't know what concat does, it's a method that's used to merge two or more arrays. It doesn't change the existing arrays, but it returns a new one. Okay, interesting. So when you take array number 1 and you concatenate with array number 2, it doesn't change array 1 or 2. It actually returns a new one, which here in this example they're calling array 3. You can see that they console log array 3 and it's got all the elements of 1 and 2 merged together. That's really cool. Great. So we're going to take our current play, which remember starts off, we invoke our recursive function with an empty array. When you concatenate it with our next play, which starts as rock, next play here is going to be rock, like that. And it's going to be passed down as the next current play. So if your brain is hurting now, that is understandable. Just walk through this step by step, and eventually it'll make sense. But this is the kind of thing that can really fry your brain. I know it fries mine all the time. So we recurse on the next play, and we're just going to keep adding these choices together forever and ever. Remember I said we need to stop eventually? What happens if we don't? Let's go ahead and step through this code really quick. So I'm going to start at the very beginning. Let's see. Oh, I haven't actually invoked rock, paper, scissors. Let's invoke it. So rock, paper, scissors with, let's say the number 2, because that's what we were working with before. So great. On the left side of the screen here, we're going to see our variables as we built them. So we have a result array, and we have a choices array. We have our recursive function, which we're not invoking yet. So the code actually skips over everything from line 21 to 33. On line 35, we actually invoke this function. This is crucial. We have to somehow start by invoking recurse. Great. We invoke it. Inside of a recursive function, we have a for loop that iterates over our choices, rock, paper, and scissors. Next play, this is where everything comes together. Let's go ahead and watch. Well, here's current play. Current play is an empty array, because remember we passed in an empty array at the beginning. Let's take a look at what next play is. It's undefined right now. But what we're doing is we are merging, that's what concat does, we're merging current play with choices at I. Now, one thing here you might notice, choices at I makes sense because it's like the string rock. However, keen watchers will notice that I put array brackets around this. That's a little confusing. So actually, if I wanted to be even more explicit about this, I could say const, let's say current choice equals an array of choices at I, like that. So the reason that we have to have an array here is because choices at I is actually a string. We need to have an array, not just a string here. So I'm going to pause this, restart it. Let's go back through. Great, now we're at the same place we were before. Let's look at what current choice is. Great. Current choice is an array of rock. And what we're going to do here is we're going to merge that current choice array, which I never changed here. Of course, that would help, wouldn't it, if I actually followed my own instructions. Let's make this current choice. Okay, now we have to start it again. Okay, so current choice is rock. It's the very first choice we have, and we're going to merge it with current play. What's current play? It's empty. It's an empty array. So next play now becomes just rock, because an empty array merged with an array that has rock in it is just rock. That's pretty cool, right? So now we're going to invoke recurse on next play. So we're actually invoking our function. This is the recursive part. we invoke it with our next play, which is the array we built. And you didn't see anything really happen, but we're actually inside the next call of recurse. So you can see, the way that you can see that is that our current play now, which used to be an empty array, is now rock. So our current choice is now going to be rock again, because we always start at the beginning of choices each time. Let's check out what next play is going to be. Current play merged with current choice, so rock and rock, is, you got it, rock rock. Okay, so now we're going to invoke recurse again. And let's just look at what's happening to next play. Now next play is rock rock rock. And if I keep doing this, next play is going to be, well, if my computer were, or if JavaScript allowed me to, it would just be infinitely long. It's going to keep growing. So we need to have our condition that says, hey, please stop recursing. When do we do that? It's this. When we reach the, I almost said root, the leaf of this tree. How do we know when we've gotten to a leaf? It's when our array that we're building is the same size as the number of throws of our game. So let's figure that out. That's our base case. So here you go. If our current play, which is the play that is the play that we are building, the length of our current play is equal to the number of throws, what are we going to do? Well, when we've reached the root of our tree, we know that we need to add this play. We need to add this game of rock, paper, scissors to our array of arrays, our result, our list of plays, which is this guy on line 18. So let's go ahead and do that. We're going to say result.push current play. So more keen viewers will realize that we're not done yet, because at this point, I'm going to push my result into, I'm going to push my current play into result, which is great. Let's see what happens when I go from here. So I start at the beginning, I recurse, I invoke my recursive function, great. Now I'm inside here on the very first one. My current play is an empty array. So current play.length is 0. So it's definitely not equal to the number of throws that I have. I enter this for loop. I've got a current choice that's rock. I make a next play, which is merging my empty array and my current choice. And I pass down next play. Great. Next play length is 1, so it doesn't stop at this if condition. And I make a new next play, which is rock rock. Okay, I recurse over this. Here we go. Now I've got my current play.length as 2, rock rock. It does equal my number of throws, and I push it into result. Now, great. Now I've got, if I go look at result, I have, it is now a length of 1. It has my very first game that I wanted to record in it. Rock rock. And that's exactly what we expected to see first up here. The problem is, now our current choice is still, or our next play, you'll see, is rock rock rock. So now we have too long of a game. The reason that this happened is because we want to go back up the tree when we hit this leaf. We don't want to keep going down the tree because we've already gotten our solution here for this one branch, rock, rock. So how do you go back up the tree? You need to tell your function to return. Or you could make this an if-else. You could say, hey, if I've got my current play and it's the right length, push it into the result. Else, if it's not the right length, keep recursing. Either way, using return or if-else, this will work the same. I like return because it looks a little bit less confusing, in my opinion. So I take away the else, and I'm just going to add a return statement here. Remember that when you return, it implicitly returns undefined. But we don't really care about that right now because we're not using the return value for anything. We're really only using this return so that we don't keep going through the function and go down recurse forever. So I'm going to take this out, return undefined. We don't worry about that. So now let's just go through our function and see if it works as intended. Okay, we're in our very first for loop. Our current choice is rock, and then our next play is going to be rock. We recurse over next play. We didn't enter our if statement. Our current choice is going to be rock again, because each time we recurse, we need to add rock, or we need to go from where we were in our loop. So rock, we can't just go straight to paper here. This needs to be a rock rock because we're okay with duplicates. Okay, next play. Great, recurse on next play. And finally, we saw that the length was correct, so we push it into our result array and we return. When we return, what happens is, let's actually see what our current, let's just see what our current play is. Our current play now, we went up the tree. It's rock now. So now we're here. We were at our leaf, and when we said, hey, function, return, we went back up the tree to rock. Now our current choice is going to be paper, because I already did 0, which was rock. Now I'm on I equals 1, which is paper. Okay, we merge our current choice with our next play. Nope, our current play with our current choice. And our next play is now rock, paper, which will be added to our result array. We can even look at what our result array is here. Rock, rock, and rock, paper. Nice. So let me take my breakpoint out, and let's just look at what the function ends up returning. Check out result now. These are all the possibilities when you have 2 as your number of throws in a rock, paper, scissors game. Rock, 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 paper, rock, scissors. Paper, rock, paper, 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 scissors. Scissors, rock, scissors, paper, scissors, scissors. And that's it. So with 2, it's not that big of a result, right? How many are there? There's 9 choices. But it quickly gets super, super big if, you know, even if you switch it to 3, you look at your result, and now it has 27 entries in it. You know, rock, 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 paper, rock, rock, scissors. So these are all the leaves of our tree, and so on and so forth. And it turns out that the formula, this is now kind of extra credit, but turns out the formula to figure out how many computations you're going to have to do, or how many elements are going to be in our final array, are you take the number of elements you have and you raise it to the power of how many throws you can have in your game. So if you have 3 elements and 3 throws in the game, 3 to the 3rd power is 27. Or, like we said, 2, right? 3 to the 2nd power is 9. And actually, if we change this to 1, what do we expect to happen if we only have the number 1 here? Well, if you only have the number 1, that means a game can only be rock, or a game can only be paper, or you can only play scissors. So I'm expecting to see only 3 elements in our array, which would be 3 choices to the 1th power, 3 to the 1, which is 3. And here's our result array: rock, paper, and scissors. More. Do I want to go into time complexity here? Maybe not. Maybe we can leave that for some other time. Here's a question you can ask yourself if you're interested. Thanks very much for watching this solution lecture to rock, paper, scissors. Have a great day.